Assalamu alaikum. I welcome you all to this lecture series on photovoltaic system. We have already discussed in the last two lectures about the very foundations of a PV cell, how the voltage and the current are related to each other. We have also seen how to model a practical photovoltaic cell in terms of the basic electrical circuit elements, and in that scenario we have discussed to develop a complete 1D model. Remember that the modeling of the photovoltaic devices is not limited to only 1D model, rather we have the 2 diode model as well as a 3 diode model. These models are more detailed and they inform us about some other processes within a PN junction which are not considered in a single diode model. The single diode model is considered more accurate and hence it will be of our interest for the rest of this course. So let us start with the today's class. So we discussed that an individual photovoltaic cell is able to produce some good amount of current, but it is not capable of producing voltage beyond a very low value, and therefore all the practical photovoltaic modules that we see, they consist of number of PV cells which are connected in series so that their combined cumulative voltage is of substantial value which is suitable for most of the practical applications. This is another PV. Let me draw the PV cells here. So the number of photovoltaic cells are connected in series, which means that their current remains essentially the same. However, by adding them in series, the cumulative voltage actually increases. So in terms of the IV characteristics, if I draw these IV characteristics here and I combine them together, for example, this is a series connection here, then this thing is connected with this module, and then this module is connected here. So this is the plus terminal and this is the negative terminal. So for this set of photovoltaic cells, if an individual PV cell has this type of IV characteristics and it is only capable of producing a voltage around 7.7 volt with a current, let us say it is 5 ampere, then if we have two cells connected in series, then their current remains essentially the same. However, the voltage becomes equal to 1.4 volt, and this follows the basic rules of the electrical circuits, where it is stated that those elements which are connected in series, they carry the same amount of current in order to comply with the Kirchhoff's current law. However, their voltage will increase such that they are summed up according to their polarities. So the complete module, which consists of all of these cells connected together, the voltage of one module or one PV module, that is equal to N times Vd minus IPV into Rs. So these PV cells, when they are combined together, they form one PV module. Nowadays, the photovoltaic modules which are readily available in the market, they have from 72 cells to 144 cells connected in series. Consequently, they are able to produce around 50 to 55 volt at an open circuit, and they are capable of producing 7 to 10 amperes of short circuit current. Similarly, the cells can also be connected in parallel. Then again, what we get on this IV characteristics is that the cells shall have the same amount of voltage. However, their current increases such that the KVL this time should be satisfied, that the voltage across the two parallel devices should remain the same, and the current from each cell, for example, this is one cell, this is the second cell, and this is the third cell. If they are connected in in parallel, then the amount of current which flows out of these terminals is a sum of the current I1, the I2 and the I3, again satisfying the Kirchhoff's current law at this node. So when we create these series and parallel combined cells and we create a module, then the next thing is that several modules are connected in series to form one string of a PV array. So let us say that we have one module here. This is module number 1. This is module number 2. This is module number 3. So if I combine them or if I connect them in series, this is known as a PV string. And if I have another PV string and I combine these two strings in parallel, then this arrangement is known as a PV array. So this is the PV array here. So array consists of parallel connected photovoltaic strings, and a PV string is known as a series connection of the photovoltaic module. A module can have all the cells connected in series, or it may have a combination of series and parallel connected photovoltaic cells. Whatever is the connection inside a PV cell, each PV module shall have its own data sheet, and that data sheet represents some important information. For example, over this IV characteristic curve, this data sheet shall have a value of the current, which is the short circuit current. It will also tell us about the open circuit voltage, which is the voltage measured when the load across the PV panel is disconnected. So we get the cumulative open circuit voltage across a particular PV module. It also tells us about some important information. This graph tells us that a point-by-point multiplication of the current and the voltage value will yield the output power of a PV module. So this output power is maximum at this point, which is known as the knee point. At this knee point, we have the maximum power because the area under this curve is the maximum. So the voltage which corresponds to this knee point is known as VMP, and the current which corresponds to this knee point is known as IMP, where this MP is used to designate that this is the current at maximum power. In most of the literature, you will also find that this IMP is written as IMPP, where the second P comes for the power point. So this point is the maximum power point. It is also known as the need point, and the current which corresponds to this value of the power is called as the IMP, and the voltage which corresponds to this power point is known as the VMP. And these four values are given on the data sheet, which is affixed on the back side of every photovoltaic module supplied by a manufacturer. The manufacturer also provides you some other parameters which are very interesting. The first parameter is the degradation in terms of the percentage change in the voltage per degree centigrade rise. It also provides us the information about the performance or about the change in the current value with each degree centigrade rise in the cell temperature. It also tells us about the percentage change in the power when we change the temperature. Now, because the temperature and the irradiance, it changes all across a day, so therefore these values which are provided by a manufacturer are given under a specific set of conditions which they emulate inside a laboratory. So that conditions are known as the standard testing conditions. So manufacturer provides us all these values. These are 4 values. So the datasheet contains the following information. So the first one is the open circuit voltage. We call it as VOC. The datasheet also provides us the short circuit current, ISC. It provides us the voltage at maximum power, usually represented as VMP. It provides us the current at the maximum power, which is the PMP. And on top of that, the value of the power here, which is a product of the VMP and the IMP. Right? So this power designates and segregates the PV modules in terms of the power rating that they can provide. Now, because as I have said that environmental conditions changes, so the standard at which these values are measured is as follows. That is cell temperature. Let me write it as the T cell. T cell is equal to 25 degrees centigrade. We have irradiance equals to 1000 watt per meter square. We also have the air mass ratio equals to 1.5. Now, other than these conditions, or a good way of checking the quality of the photovoltaic cell is to measure the fill factor. Now, what is the fill factor? Fill factor states that if we have our given set of values given in a data sheet, ISC, IMP, VMP, VOC, then the fill factor tells us the ratio between the VMP, IMP and the VOC into ISC. And for an ideal system, it should be equal to 1 so that we get the maximum value out of it, but it is not possible to make it equal to 1. For most of the photovoltaic cells which are available, they are made up of silicon. So for silicon, the value of the fill factor, the value of the fill factor is between 0.7 to 0.75, and for multi-junction amorphous silicon, let me write it here, multi-junction amorphous silicon, the fill factor ranges between 0.5 to 0.6. It is a very good way of establishing the quality of the manufacturing and the quality of a given PV module. So now that we have seen that for a given PV cell, we combine them together to create a module, and the module is then the basic unit for designing a given PV system, because everything just from the string level to the array level, everything is based on the sizing and the power rating of, and the performance and the power rating of the individual PV module. So therefore, it is essential to understand that how to establish the impact of the varying temperature and irradiance on a PV module level. So we have already seen that the increase in temperature happens, then the voltage of a given PV cell decreases, and this decrease is for most of the silicon based PV modules, it is about 0.37% per degree centigrade change in the temperature. And it is because this voltage is dropped, so this is usually written in terms of a negative sign. But as we increase the temperature, the current I also increases, but this is also for this is a very limited amount of change, and that is about 0.05% per degree change in the centigrade, which means that if we have a change in the temperature, then the overall power of a PV module reduces, which implies that the performance of a PV cell or a PV module, its performance is better in winter compared to the summer, where we think that abundant amount of light is available and its intensity is also available, but because of the high temperature inside the PV module, the output power of a PV module is less in summer compared to the winter climate. The datasheet values of a PV module, they are seldom met in real life conditions, so manufacturers provide us another important information which is known as an NOCT value. NOCT value is the nominal operating cell temperature, which corresponds to 45 degrees centigrade of a cell temperature, or in some cases it is 25 degree ambient temperature, which is the climate difference here. So if we have the NOCT value available, let me write it this as NOCT value, which is the nominal operating cell temperature, and this is measured at 800 watt per meter square at 25 degrees centigrade ambient temperature. We have this NOCT value for a given PV module, then we can calculate the cell temperature equals to T ambient plus NOCT minus 20 degrees centigrade divided by 0.8 into irradiance, and this irradiance is in kilowatt per meter square. And if we do not have the value of the NOCT for a PV module, then there is another expression which can give you cell temperature, and that is equal to T cell is equal to T ambient plus gamma G divided by 1 kilowatt per meter square, where this gamma is it ranges between 25 to 35 degrees centigrade, and it is just a factor here. These two equations, they provide us another important point, that at any given irradiance G, the cell temperature is usually 25 to 35 degrees centigrade higher than the ambient temperature. So now that we have seen some of the parameters of a PV module, let us discuss about the data sheet of a practical PV module, and we will see what additional information is available in it. I have opened up a data sheet for this PV module. This PV module is manufactured by JA Solar, and this is just used to demonstrate the features which we have already discussed. We will try to find out those values for this PV module. This PV module is a 290 watt monocrystalline 60 cells module, which has 30 watt greater than the average power rating. It is claimed by this module manufacturer. So if you open up this module, we have engineering drawings available here, and this engineering drawing is providing us some information about its dimensions, which are useful when we design a PV plant, because for each mechanical parameter that is available for a PV module, we need to design the stable structure. We also need to design the mechanical structure consisting of the C channels and the cable trays and some related stuff. So this provides us the information for the power plant sizing. As you see here, it is a 60 cell PV module, which means that it should contain 60 cells here. So if you see here, this is one cell, and then we have, this is cell number 2, this is 3, 4, 5, 6, 7, 8, 9, 10, and also we have 2, 3, 4, 5, 6. So there are 60 cells available in this module, and these cells are individually, you can identify that this one block is corresponding to one cell for this module. Other than that, we have these two leads available that corresponds to the output terminals, which is one is positive, another one is negative. This is known as the junction box. We will shortly revisit this data sheet once we go through the next topic, which is on the shading of the PV panel. Other than that, we have the packaging information for this module, because once it is shipped from the manufacturer's side, they are stacked in the wooden boxes, and each boxes contains 30 panels, and we call it a pallet. So 30 panels per pallet are here. This junction box contains these diodes. As I have said, that we will shortly revisit this PV module datasheet again, and we will identify what are these three diodes for. It has a maximum system voltage equals to 1000 volt. This is also important in the design of a PV plant, and we will discuss it when we will move forward with this course. In here we have electrical parameters. Let me zoom in a little bit. These electrical parameters are providing us values for this 280 watt PV module, 285, 290, 295 and 300. So with a difference of few watts, 5 watts, 5 watts here, this datasheet is meant to cover all of these 5 models designed by this manufacturer. And with this, it is providing us the rated maximum power at STC, and this STC is written here as 1000 watt per meter square irradiance. Cell temperature, this is very important, cell temperature equal to 25 degrees centigrade, and an air mass ratio equals to 1.5. So this is your PMP that we have discussed a short while ago. Then we have the open circuit voltage VOC. It is this value 39.05 volt. Maximum power voltage, which is VMP, it is 31.60 volt for this 280 watt module. Then we have the short circuit current value for each of these models of JAM, and it is in amperes, 9.38 ampere for 280 watt, and for 300 watt it is something equals to 9.75 ampere. Then we have the current at the maximum power. So it designates as maximum power current IMP, and this is 8.86 for 280 watt and 930 for this 300 watt module. Then this module efficiency is also given. It is 17.12 at the current time. We have some modern PV modules. They are able to produce an efficiency more than 20 watt. So this has a module efficiency equals to 18.35. Remember that this module efficiency is not the cell efficiency, and it is less than the cell efficiency because of the additional cabling required to connect two different cells. And there are other parameters involved in the designing, because not all the area is covered, and therefore the module efficiency is usually less than the cell efficiency. And for these very reasons, the module efficiency is of importance when we design a given PV plant. Then it has a power tolerance from 0 to plus 5 watt. Temperature coefficient of ISC, it says that it is 0.060% per degree centigrade. So if the cell temperature is 25 degrees centigrade and we have a rise in this temperature, it goes on to 26 degrees centigrade, then the current value of the ISC, these are the ISC values, these values actually increase by 0.060% for 1 degree centigrade rise in the cell temperature. It is not the ambient temperature, it is the cell temperature. And also this is the VOC. You notice here this, we have a negative sign here, and this negative sign shows that the voltage shifts here when we have an increase in the temperature. Then this PV module datasheet is providing us the value of the Pmax, and it is also having a negative sign here, which means that the power actually decreases when we have increase in the temperature values. You should also notice here there are three important symbols used to designate each of them, and it is this alpha, this beta, and this gamma. Gamma corresponds to the change in the percentage change in the maximum output power with the increase in the cell temperature, while the beta and the alpha are for the voltage and the current respectively. If we see here, the manufacturer has also provided us a set of waveforms for different irradiance values. So at 1000 watt per meter square irradiance value, it has shown its curve, and there are 5 different curves here that correspond to 1000, 900, 600, 400 and 200 watt per meter square irradiance. It also provides us the PV characteristics, which are the power versus the voltage. So here we have the power, and here we have the voltage. So these power characteristics are also drawn, correspond to those 5 distinct irradiance values: 1000, 800, 600, 400 and 200. So we have 1, 2, 3, 4, 5. So at these 5 distinct values of irradiance, the manufacturer provides us the performance of this PV module. Other than that, we also have the NOCT, the parameters at NOCT values. Now these NOCT values, it is stated here that this is under the normal operating cell temperature. So the irradiance is 800 watt per meter square, spectrum air mass ratio 1.5, ambient temperature equals to 20 degrees centigrade, and a wind speed equal to 1 meter per second. And this wind speed is very important because, for example, if this is a PV module, so we have wind which sweeps over the surface of this module as well as on the backside of the PV module. Consequently, it actually helps us in lowering the cell temperature for a given PV module, and therefore this wind speed is an important practical aspect which is not considered in the indoor testing of the standard testing conditions. So under these under these NOCT values, you can see here that the visible changes are there. This 280 watt panel, which was previously producing 280 watt at standard testing condition, is capable of producing 204.71 watt at the NOCT conditions. The open circuit voltage has also dropped from 39.05 volt to 35.81 volt. Similarly, we have the short circuit current value dropped from 9.38 ampere to 7.64 ampere of the current. So these are some of the typical information which is given on a data sheet, and most of these informations are enough to design a given PV power plant. The information which is not given in this PV data sheet is the RS is not given here. We also do not have the parallel resistance about this PV module. The junction, PN junction, and the ID is not given here. The reverse saturation current of the cell is not given in this data sheet. We also do not have information about the IPH value or the photo generated current value, which is the ISC in the model that we have discussed in the last class. So these 5 parameters are not given in this data sheet, right? And for this, we have already explained various procedures are available to identify these things, and these things provide us a very accurate measurement of the plant performance in terms of using the computer aided simulations. So now that we have seen the data sheet of a PV module under the NOCT and this STC value, let us discuss and let us bring in some complexity in the system analysis. So we said that the ideal PV module is not capable of figuring out the behavior of a PV module under the shading conditions. So now by using the practical 1D module, we will identify how a PV module will exhibit and how it will showcase its performance if we have shading on one part of the PV module. So first of all, let me tell you what is actually the shading. So suppose that we have PV cells which are connected in series. So they are connected in series. This is cell number 1, and we have this is the nth cell. Now these cells, if we see, they are capable of producing a certain amount of current if we have some load connected here. So everything is okay. They are producing amount of current. This current is supplied to this load. Consequently, we have the voltage produced across this load, and some power is drawn by the by this load here. Now shading implies that, suppose that we have a cloud over this part of this PV module. This means that out of all the shells or all the cells of a given PV module, this part is shaded because we have a cloud over here. Or it could be some person who is standing right beside the PV panel. It could be a civil structure, some telecommunication tower, which is casting its shadow over the PV module, and as a result of that, these two modules are now shaded, and therefore they are not producing the same amount of current as required by these PV cells. So this current I, which is the shaded current, and we have the current I, let us say H, which is the healthy current or an unshaded cells current. These two currents are now different, and we need to identify the impact of this difference on the PV cell, and then how to get rid of and how to mitigate the performance degradation using some technique. So this is what I will now talk about. So let me draw the draw a PV cell model here. So this cell can be modeled as, this is the RS. Here we have the ISC. Right here we have the diode ID, and here we have the parallel resistance RP, and this corresponds to one cell. Let us say this particular one cell, and it is connected with the all other cells, which are, let us say this is n-1. These are n-1 cells here. So all of these cells are the n-1 cells, and they are actually combined to a load in which the current I is actually flowing. So this is the V, this is some resistance R. Now the current which is flowing through those cells which is unshaded, I have accumulated all the unshaded modules into a single block here. So the current through this n-1 cell is this IPV, and the voltage here is Vn-1, and across this shaded PV cell, we say this is the plus, this is minus, and this is the VSH. So the voltage across the shaded cell is designated as VSH, while the voltage from the rest of the cells which are not having any kind of shading is equal to Vn-1. These unshaded cells are putting in the IPV current into this cell. Now this cell, if you see this ISC is not the same as this IPV. So what happened is that some of the current is diverted through this parallel branch, which is this RP, and when it goes through this parallel branch RP, it routes itself through this side, and consequently by flowing through this RS, it becomes the load current I. Now if I apply the Ohm's law, here, then the current which is flowing here, it is producing a voltage in this direction. So this is positive, this is negative, and consequently this ID will be equal to 0 because this diode is not reverse biased. We have plus sign here, we have a negative sign here, and this is enough to reverse bias this diode. So the current will flow through this parallel branch here. Consequently, it shall have a voltage equal to V is equal to IPV into this RP. Now this current then moves into this RS, also creating this plus sign, and here we have the negative sign here. So consequently, the net voltage across this shaded photovoltaic cell is this side positive and this side negative, right? This implies that a cell which is shaded is actually not adding into the voltage value, rather the voltage across a shaded cell is subtracted from the overall voltage, which brings down the power output of the load. So what is the VPV here? VPV, which is equal to n minus 1 minus VSH, because it has a different polarity here. So this is equal to Vn minus 1, and this V shunt is the current IPV into Rs plus Rp, where this Vn minus 1, that is equal to n minus 1 over n into Vpv, and this n is the number of cells which are not shaded. So the net change in the output voltage delta V is equal to the total voltage supplied by the unshaded cells minus the voltage of the shaded cell VSH, and that is equal to VPV minus 1 over n into VPV plus IPV into Rp plus Rs. And this can be further simplified by assuming that this Rp is greater than the value of this Rs. So if we do this, then this delta V is approximately equal to VPV over n plus IPV into Rp, and this is the net change or the difference in the output voltage if one cell is shaded in a PV module. In fact, the problem is far more complicated than the overall reduction in the output voltage. Is this amount of voltage VSH which is producing across this cell. So the current is flowing through here, and this current is substantial, provided that this is quite a low value, and we have some 8 to 10 ampere current flowing here. And these two resistances, when comes in series, they produce or they dissipate all the power in terms of heat, and that heat can damage the shaded PV cell. And this process or this damage is known as the hotspot. So the first problem with this shading here is that shading can cause hot spots on the shaded cell, and this hotspot means that the cell can be permanently damaged. It can permanently damage the PV cell. So cell is important, and we need to safeguard that cell. So let us see how we can safeguard a given PV cell against the shading condition. The solution here is very simple, that on a group of PV cells, over a group of PV cells, a diode is connected in parallel. So if we have some voltage developed across a shaded module or across a shaded cell, then the diode will turn on automatically, thereby protecting the cell. And this diode is known as the bypass diode. And usually each bypass diode is connected on a group of 18 to 24 PV cells. It's a usual thing. However, depending on the larger PV panels which are available now, they also have 3 diodes in them, which implies that every 48 cells have have a bypass diode connected over them. So let us see how a practical PV module is actually wired. So for that, I will go back to the data sheet here. In this data sheet, okay, so we have this is cell number 1. It is connected in series with this cell number 2. It is connected with this cell number 3, and so on and so forth. So here we have, this is cell number 10, and this cell number 10 is now connected with this cell number 11, and this is the overall scheme of the connection here. So we go down, and then we move up, and here these are all connected like this one. And over here we have the two leads which comes out. This is negative, and this is positive, and this side is negative. Now we want to safeguard a group of diodes, a group of cells in case of the shading condition, and therefore we have these as well, right? So 1, 2, 3. This is 1, 2, 3. So we have made connections like this one. So this is connected here, and here we place a diode. Here we place a diode. This is one diode, and then we have another diode here, right? And then we have the third diode available here. So these are now the outputs plus sign, and here we have the minus sign. So this is diode number 1, this is diode number 2, and this is diode number 3. Now these 3 diodes, they are absolutely not playing any role when we do not have any shading conditions, because for these diodes to turn on, they have to have a potential difference equals to the greater than the turn on voltage. I will show you what kind of diodes are used here. They are normal diodes based on the current rating. Their normal line rectification diodes are used. We do not require to have a very fast switching diodes here, because the changes which comes in the cell, they are not very rapidly changing conditions, because cell temperature rises slowly and its gradient is not very sharp, and therefore normal ordinary line rectified diodes are used in most of the cases. So these 3 diodes are essentially turned off, and therefore we do not have any problem with the output power of a PV module. Now suppose that we have a shade here. So let me create a shade here. Let us say that we have a shade on this side of a PV module. So now this is shaded, and therefore it will develop negative voltage across itself. These group of cells shall have some negative voltage, and as we have the negative voltage available, then this diode will turn on. When this diode will turn on, then this point becomes positive, this becomes a shorted path. So we have the overall PV panel will have this type of a connection here. So it will go here, it will go back to this point. So this becomes positive and this side becomes negative, consequently safeguarding this group of cells here. This information is also given here, that we have 3 diodes available. These 3 diodes per panel, which are placed in the junction box, and this junction box is placed right beside or on the back side of a PV module. Now these junction diodes are 3, which means that every 20 cells that I have designated here, so 1, 2, 3, 4, so these 2 have one diode, bypass diode, these 2 have another bypass diode, and the last 2 have the third bypass diode. Each of these 20 cells have one bypass diode connected here. And when we purchase some non-standard photovoltaic panel which are available in the market, we always need to check the presence of the bypass diode, because sometimes they are not present in the junction box, which means that your panel is prone to the hot spot in case of any shading over its group of cells. Now one thing is for sure, that if we have a shading happened on a PV module, then a substantial, or 1/3, in this particular case 1/3 of the cells are short circuited, which means that they are not producing any amount of power. So the point here is that this is actually a loss, but this is essential in order to safeguard the PV cells. Let me write this here as that with bypass diode activated, the output power of PV module reduced. So what is the solution here? Well, ultimately, there are two things. We can have a diode connected across every cell of a PV module, but that's not only increases the cost of the system, but it also add complexity in the manufacturing processes. Fortunately, some of the companies like Jingli is actually producing smart PV modules that have bypass diode across each PV cell, which means that if we have shading on only 2 cells, then instead of getting rid of the 20 cells for this PV module that we have studied, only those 2 cells will be bypassed. Consequently, it will not pose much change in the output power ratings here. Now this particular shading phenomena can now be summarized in terms of the PV module. So we have this PV module, and we have a diode here. For the rest of this course, we will discuss the PV system based on one diode per PV module, because the concept is essentially the same. If we have 3 diodes connected in this PV module, it means that we can represent it in terms of 3 PV modules with one bypass diode connected across them. So this diode will only work in the shading conditions. In the non-shading condition or in the uniform irradiance condition, this diode essentially remains turns off, so all the current flows through this PV module. So this is one important thing that I want to elaborate here. So there is another perspective of understanding the physics of shading in a PV module, and that is in terms of the IV characteristics of a PV cell. So we said that in a given PV cell, we have this diode to represent the PN junction, and then we have this RP and this RS. And we said that this is a constant current. Through the diode, we have an exponential current which is governed by the Shockley diode equation. And if we subtract these two together, then we get this type of a characteristic curve. Now on the other side, this diode has this type of a characteristic curve. So if we subtract this side, which corresponds to the negative current value and the negative voltage value, then we end up with this type of the curve for a PV cell here. Now suppose that we have 2 cells connected here. One is this one, and let me draw it here somewhere. Okay, and we have another cell connected here, and this red cell is under the shading conditions. So one of them is under the shading condition. So we have, let us say this is I. It corresponds to this I2. This is producing the current I1, and here we have the voltage V here. So suppose that we have this current I2, and the current from a shaded cell is something like this one. Here we have the, okay, right. So this is the current for this I1 here. Now suppose that I have a load connected here, and this load is, I am wearing this particular load, right? If this is the operating point of this load, so with this means that this current I2 can supply this current at this value, which is equal to V2. However, I1 is not able to produce this much amount of current in the positive side, so it will go. However, it can provide this amount of current at a value which is this V1, and this V1 is negative. So the overall voltage at this output V becomes equal to V1 V2 minus V1, right? But with this negative voltage here, if we do not have a blocking diode, it will operate in the negative voltage, and consequently this is the same thing what we have studied just a while ago. So V is equal to V2 minus V1, and consequently the net voltage across this module becomes less than the sum of the voltage V1 plus V2. However, because of this shading, this is the actual voltage available across this particular load. Similarly, we can also understand how if we have two panels which are connected in parallel, or if we have two cells which are connected in parallel, what happens if we have a mismatch among their characteristics. So suppose that we have one PV cell and we have another PV cell, and they are both connected in parallel and they are supplying some current to this load. Then this is current I1, this is current I2, and their sum is actually I1 plus I2, provided them they have the same voltage here. So suppose that they have this type of a characteristic curve, and this characteristic, and one of the panels has a characteristic curve, something like this one. So let us say we are at this point P1, and this we can do by adjusting the value of this resistance R. So this is P1. At this value of P1, we have the voltage here, and that voltage is the same. However, we have the difference in the current values. So if for this is the I1 and this is I2, then we have the total amount of current supplied here is the sum of this I1 and this I2. Now, if I move further and I move to this particular point, this is P2, then what happened here is that the current of the I2 actually decreases, right? So we have now the current is I1 plus I2, but this is less than this sum here. So this is less than this sum here. So I1 plus I2 is greater than the I1 plus I2 at point P2, and then we move further to this point. We decrease the load. So when we decrease the load, we move on to this point P3 here. At this particular point P3, you see that this current supplied by this I2 is equal to 0. So at P3, I2 is 0, so we have only I1 available here, and this is greater than this I1. Now, if I increase the load further and I move on to this point, let us say this is P4, then this I2 is not able to provide any amount of current. Rather, it will go on to the negative side and will try to catch up this much amount of current at some negative value of the current I, which implies that if we have this condition, or the load is set such that we are at this P2, then not all the I1 flows through the load, rather some of the part will circulate through this current I2. Consequently, the current flowing through this load R is less than this current I1, which was previously supplied by having the load set at the point P3. If we further increase the load, then it will happen that we have I1 becomes equal to I2, and consequently the current I flowing through this load will become equal to 0. So in order to safeguard this circulating current between the two parallel connected PV cells or the modules, a concept is known, which is a diode is used, and that diode is known as a blocking diode. So blocking diode concept is used to stop the circulating current between parallel connected PV modules, because it seldom happens that we have a blocking diode present in a PV module if any module has some parallel connected PV cell. So it is usually this blocking diode concept is applied on a module level, and therefore each string of the PV modules is supplied with this diode here, so that we do not have any circulating current between these two parallel connected strings here. So here we have the load RL. This is the string 1. Let us call this one M11, this is M12, this is M21, this is M22, this is M2, M31, and this is M32. So this string and this string, they have these they have these blocking diodes here. So the overall array, whenever we study an overall array, we simplify it something like this, that we connect diodes across in parallel with each of the module, and these diodes are known as the bypass diodes, and the blocking diodes are supplied in a string level, not even on a module level. It is provided at a string level to eliminate that no current flows through on this side if we have any mismatch because of the environmental conditions. And usually this happens because of the change in the temperature values. So with this thing in mind, we will stop this lecture here. So see you in the next lecture. Take care. Allah Hafiz.